Okay, so now the final remark before we move on to phase transitions, which is the next lecture. And this is about how to calculate, in this case I'm going to talk about internal energy and entropy, but really you can calculate any thermodynamic potential for any system of which you know the equation of state. So imagine the equation of state, completely generic. It doesn't have to be an ideal gas or a van der Waals gas or anything like that. If you know that, then you can always integrate any thermodynamic potential you like. For instance, if you want to express energy as a function of volume and temperature, which you can do, and this is what is solved in the lecture notes, what you have to do is to express the differential of the potential that you want, in this case energy, as a function of the variables that you have chosen to be independent, in this case temperature and volume, and reduce any derivatives that appear. Okay, so in this case, this derivative we have seen already. This is just the heat capacity at constant volume times dt, and this derivative over here we have already made the example in previous video of this lecture, that this reduces to the thermal pressure coefficient, which is this derivative here, multiplied by temperature, and here is minus p dv. Okay, and we simply integrate this. The only thing we need to get out of the equation of state is this derivative. Okay, so I just want to make one practical remark. It may be the case, okay, that from the equation of state that you are given, for instance, like in this form, it may be the case that it's easy to write p as a function of t and v. Okay, in this case, you just do that and take the partial derivative and express the result as a function of t and b to be able to integrate it. However, it may not be the case that it's easy to do this. Okay, so in that case, what do? Well, you can always resort to the cyclic property of the partial derivatives, and you can always put this derivative differently. Okay, so you can write this as minus the partial derivative of volume, in this case with respect to with respect to temperature at constant pressure, and in the denominator partial derivative of volume with respect to pressure at constant temperature. And perhaps, okay, I'm just saying that it could be the case that from the equation of state that you are given, it is easier perhaps to write v as a function of t and p, in which case you can calculate each of these two derivatives and then take the ratio of the two, and then you get the thermal pressure coefficient. You plug that in here, and what you do in the end is to just integrate, okay, between the two equilibrium states that you are interested in. So the internal energy difference, which is uv minus ua, is going to be, well, the integral from Ta to Tb of the heat capacity at constant volume as a function of temperature, which usually is a function of temperature, and then plus the second term. Second term, as we had said, well, this would be the integral from initial volume to final volume, because there is a dv here, of T times the thermal pressure coefficient, so this derivative, just no, that's with respect to temperature constant volume, minus p, okay, where p has to be written as a function of v and t, because these are our independent variables, and it's understood that this derivative is also expressed in v and t, so that we can make the volume integration here. Okay, so this is how you would get the internal energy, but I emphasize you could have any thermodynamic potential, and the whole point is that you have to select the variables you want, write the differential of your potential in those variables, and reduce any derivatives that appear there, and then carry out the integration after calculating any coefficients you need to calculate from the equation of state. So I hope it's clear, the procedure in general. Okay, and the same thing would work for the entropy. Okay, so imagine I want entropy as a function again of temperature and volume. What you need to do is partial derivative of s with respect to t at constant v dt, and partial derivative of s with respect to v at constant t. And in this case, this is nothing but 1 over T in this case, heat capacity at constant volume, differential of temperature, just by the definition. And here you have one of these derivatives that you have to use Maxwell's relation to solve, because you see entropy appears in the derivative, but what is kept constant is not pressure or volume, so you cannot make the heat capacity at constant pressure or volume appear somehow here. And you know that here you have to go look at the second Maxwell relation, and from there you find that this is nothing but the same thing we had before, the thermal pressure coefficient. Okay, and once again, evaluating this, you will have to do it from whichever equation of state you are given, and you have to choose wisely whether to make this derivative or perhaps make this derivative and then take to the minus 1, or perhaps try to break this derivative down into, like I said before, partial derivative of volume with respect to pressure, with respect to temperature at constant pressure, divided by minus partial derivative of volume with respect to pressure at constant temperature, like I wrote here. Okay, so it's either one or the other way, it should work out. So there's always one way which you can do it. So we are going to do this for the van der Waals gas, but like I said, this is general and you can express any potential you like. Okay, these guys. And also the entropic potentials as well. Okay, or any other made up potential. So this is quite useful to practice, and you may challenge yourself to calculate these guys, for instance, for the ideal gas or for the van der Waals gas. That's a nice exercise to practice. So this concludes this lecture of liquefaction of gases, and I'm going to now move on for the next lecture, which is phase transitions.